Welcome one and all. We are still introducing limits with our second part to the numerical approach. In our previous video, we had seen that as x approaches 2 from the left, 9x over x squared plus x approaches 3. And that as x approaches 2 from the right, 9x over x squared plus x approaches 3 as well, which allowed us to conclude that disregarding the side from which we're approaching, as x goes towards 2, 9x over x squared plus 3 is equal to 3. The question that was left unanswered was, why can we not simply compute f at 2, which is 9 times 2 over 2 squared plus 2, 18 over 6 is 3, rather than going through the tedious process of computing left and right-hand limit approaches. Let's look at two more examples that will highlight the distinction between a limit and a function's value. Here's example number 1, which asks us to compute the limit as x approaches 1 for f of x, where f of x is defined as the quotient between 2 minus root of x squared plus 3 and x minus 1. Right from the beginning, you'll notice that f of x is not defined at x equals 1 itself. In fact, f at 1 is simply undefined, or DNE. Observe, however, the limit as x approaches 1 from the left. So, as we've done in our previous video, I have let x approach 1 from the left, which is the left-hand column. So x started from 0 and progressively is getting closer to 1. And the resulting value of the function for this sequence of values seems to be approaching minus 0.5 or minus a half. You would probably agree that there is a pretty significant trend developing in the sequence of numbers that you just saw, and that the values are getting closer to minus 0.5. And so we can assume, not without some risk, that the limit as x approaches 1 of the quotient 2 minus root of x squared plus 3 over x minus 1 does equal minus a half. Let's now observe what happens when x approaches 1 from the right. Once again, we've developed a sequence of numbers, so under column x, where those numbers are approaching 1 but are systematically to its right. Notice how f of x has values that seem to be approaching the fraction minus 0.5. So the same trend as x approaches 1 from the right occurs as it did for x approaches 1 from the left. The values of f of x are once again getting closer to minus 0.5, and so we can assume, again with a certain degree of confidence, that the limit as x approaches 1 of 2 minus root of x squared plus 3 over x minus 1 equals minus a half. Given that both the left-hand approach towards 1 and the right-hand approach towards 1 agree, then we're confident in saying that the limit as x approaches 1 of 2 minus root of x squared plus 3 over x minus 1 equals minus a half. In this example, the function f of x is undefined at x equals 1, and yet our limit process has allowed us to find an existing value of minus 1/2. This just goes to show that direct substitution may not be the best method all the time. Here's what's happening graphically. So the function's value at 1 does not exist. However, the limit process takes us towards minus a half, whether we approach from the left or from the right. Here's example number 2. Consider the limit where x approaches 0 for f of x, where f of x is the function e to the power 1 over x. Once more, you'll notice that f of x is not defined at x equals 0, which is where we are using our limit approach. So f at 0 does not exist. Observe the limit, however, as x approaches 0 from the left. So the sequence of values that were chosen for x are left of 0 but progressively getting closer to it. The outcome of the function's value for these selected values of x is becoming smaller and smaller and tending towards 0. So we're quite confident in assuming that as x approaches 0 from the left, e to the 1 over x is heading towards 0. The surprise occurs when we observe the limit as x approaches 0 from the right. So this time, I started off with a value of x which was 1 and am getting systematically closer to 0 in my choices of x, but remaining to the right of 0. The outcome of the function's value is growing quite rapidly, as you can see. I dare you to even try to pronounce the size of f of x when x is 0.01. I think it would be reasonable in this case to conclude that as x approaches 0 from the right, e to the 1 over x is heading towards infinity. In this last example, the result clearly depends on the side from which the approach is taken, and there is no specific result to describe the trend on 1 over x, e to the 1 over x, as x approaches 0. Therefore, we have to say that the limit as x approaches 0 of e to the 1 over x is undefined. The function e to the 1 over x is undefined at x equals 0, as is its limit. This did not prevent, however, the left-hand limit from being defined. So you can see how there are certain contradictions between what our limits can produce as results compared to what the function's values can result in. So graphically, here's what took place. We have a function that is undefined at 0. We have a left-hand approach towards 0 that makes the function's values become 0 as well. And we have a right-hand approach which is throwing our function towards plus infinity. This is what we would consider being an asymptotic behavior. So what should you retain from the last few examples? Well, the function's value, or its mere existence at x equals a, can be potentially different from the limit's value, or its mere existence as x approaches a. Possibilities include, like in this picture, a situation where f at a exists, but the limit does not because of conflicting left and right hand results. You could also have f of a that exists and the limit that exists, but that they don't agree. Here notice how the value the function approaches as x is getting closer to a is not where the function's definition is placed for a value of x equals a. Quick note on the numerical approach. So the numerical approach can be tedious, and although straightforward, it can also be unreliable at times. For instance, let's suppose we wanted to evaluate the following limit, where x is approaching 0 from the right and applied to the function sine of pi over x. What impression would you get if you had done the following numerical approach? So on the left, values of x have been selected progressively getting closer to 0, yet remaining to its right. So x is definitely heading towards 0 from the right. When replacing x by these numbers in sine of pi over x, look at the outcomes, which are systematically giving values of 0. Well, the fact of the matter is that in reality, the function oscillates faster and faster as x approaches 0. It's really just a coincidence that our choice of iterations landed on the zeros of the function. This function's limit doesn't exist.